characteristics of polynomial functions. Let's talk about the behavior first. We've got both increasing and decreasing intervals in this example that's drawn right here. Okay, so when is a function increasing? As we move from left to right, if your graph goes up, that's an increasing interval. And as we move from left to right, if your graph goes down, that's a decreasing interval. So if you look at this graph right here, we have an increasing interval here, and we have another increasing interval here. The only decreasing interval happens right in the middle. Okay, so if you have them, I would encourage you to grab some highlighters, two different colors. Make sure you highlight your decreasing interval one color and your increasing intervals another color. And you can use those two colors for the entire worksheet if you want to. Now, when we're talking about increasing and decreasing intervals, we always label these intervals using their x values. So this example right here, we move from left to right. So how far left is this graph going? Well, if this extends forever and ever and ever, hopefully you can see that it goes left forever, okay? It's inching out slowly, but it will go forever to negative infinity. So I'm gonna place negative infinity over here on this side of my x-axis. And then if this graph continues to increase, it is going up, but it is also inching its way to the right forever. So I'm going to go ahead and use positive infinity on this side. So let's talk about these increasing intervals. If we start at negative infinity and we move all the way to this local maximum right here, what is the x value that we see? It's a -2. So our increasing interval goes from negative infinity to -2. And we use parentheses here when we're talking about increasing and decreasing intervals. Now this decreasing interval right here, it begins at -2 and it finishes at +2. Again, we're always writing these intervals using our x values, and we always go from left to right, least to greatest. So our function is decreasing from -2 to +2. And then this last section of my graph is increasing again, and it starts at this minimum value of 2, -16. Again, we're always using our x value. So from 2 all the way to positive infinity, our function is increasing, okay? So let's look at our end behavior now. What's happening on the very, very, very far left side of our graph, and what's happening on the very, very, very far right side of our graph. Now, Miss Wynn did a great job of creating this for you. She even color-coded it for you, so if you have highlighters, again, I'm sure your copies are in black and white, so go ahead and use a highlighter or a marker, colored pencils, whatever you've got. So if the degree of your polynomial function is even, and remember, degree is your highest exponent, if it is even, then your end behaviors go in the same direction, okay? Let me write that down right here. If your end behaviors, let me start over. If the degree of your polynomial function is even, your end behaviors go in the same direction. Okay? If the degree of your polynomial function is odd, so if the highest exponent is an odd number, then the end behaviors of your polynomial function go in the opposite direction. Odd, opposite. All right? Odd, opposite. That's how I always remembered it. Okay, so let's go back to our even degree polynomial functions. I know they end in the same direction, so the question is, do both ends go up or do both ends go down? Your job next is to look at the leading coefficient. If the leading coefficient is positive, both of your end behaviors are going to point up. If the leading coefficient is negative, then both of your end behaviors are going to point down. Okay, so let's look at these examples right here. So I'm going to highlight, we'll just use orange here. So our top example is y equals 2x squared minus 3x plus 5. oops, I need a highlighting tool, not a marker. Here we go. So 2x squared. So I know that the degree is even. That means my n behaviors go in the same direction. And then I say, okay, well, my leading coefficient is positive. That is why both n behaviors go up. If you look at your second example, the bottom example here, y equals negative 3x to the 6th power plus 3x cubed plus 5. Again, it's an even degree polynomial, so the n behaviors go in the same direction, but our leading coefficient is negative 3, so it's a negative leading coefficient, meaning both of my n behaviors go down. All right, so now let's look at odd degree polynomial functions, odd opposite. So if the largest exponent is odd, they're going in opposite directions. But how do you know which way is going up and which way is going down? Well, I kind of like to think of it this way. So we have 2x to the 5th power. So those are obviously going in opposite directions because the 5th power is an odd exponent. But my leading coefficient is a positive 2. So if I were to connect the two ends of my graph, if I were just to connect the two ends, I would have a positively sloped line, right? That's how you can remember the left side goes down and the right side goes up. If you look at the second example, it says y equals negative 2x to the 7th power. So we have an odd degree polynomial and our leading coefficient is negative. Our leading coefficient right here is negative. So if I were to connect the two n behaviors, I would have a negatively sloped line. So that's how you know the left side is up and the right side is down. So look at this example right here. Without even knowing what the equation is for this function, if I were to connect my two end behaviors, they're going in opposite directions. So I know this has to be an odd polynomial function, okay? And because the slope of this line is positive, I know the leading coefficient is also positive. Hopefully that makes sense. Now, down here, we have our n behavior notation, okay? So as our x value approaches negative infinity, that's what that arrow means, approaches. As our x value approaches negative infinity, because remember, we can never actually reach a negative infinity, our function value, f of x, is approaching positive infinity. So as my graph goes really far to the left, its height is going really high. Okay, that's what that says. Now as our x value is approaching positive infinity, our function value, our f of x, is also approaching positive infinity. So both sides of our function are going up forever. They're both approaching positive infinity. And what's nice is you're always going to use this as your starting value, like your sentence stem, if you will, okay? As x approaches negative infinity, f of x is approaching blank. As x approaches positive infinity, f of x is approaching blank, okay? Same is true down here. If we know both of our n behaviors are going to negative infinity, then fill in the blank. Both of these are negative infinity. And it's lovely because our sentence stems over here are exactly the same as well. As x approaches negative infinity, f of x approaches blank. As x approaches positive infinity, f of x approaches blank. It's going to be the same thing over and over and over again. It's kind of a lot to digest, but I want you to stop and think. There's no reason for you to go through these super fast. Just stop and think about what your function is doing. But that's how you pronounce those words. It might help you also to remember that f of x is the same thing as saying y. What is the y value, the height of your graph doing? Don't forget f of x and y are synonyms, and your y value is just the height of your graph, how high up and down it goes. All right, so let's talk about domain and range. Remember from algebra, domain is all possible x values of a given function, range is all possible y values of a given function. So when you have, let's talk about domain. For every single polynomial function, your domain is always going to be all real numbers, always. The domain of a polynomial function, unless you restrict its domain, which is not what we're talking about right now, the domain is always going to be all real numbers, okay? Set builder notation is listed first here for you, and this is red. X is an element of all real numbers. All right, that's how you write it in set builder notation. What does interval notation look like? It just goes from negative infinity to positive infinity. And we always use parentheses around an infinity. The parentheses represent you're getting infinitely close to that value, but you can never actually reach it. So we're always going to be using parentheses when we talk about infinity for our domain values, right? The same is true here. If we have an even degree and a negative leading coefficient, our domain is still going to be all real numbers. If we have an odd degree polynomial function, our domain is still always going to be all real numbers. Like period, end of story. It goes left and right forever. Okay? Now let's talk about the range of a function. The range of a function. If you have an even degree and a positive leading coefficient, you need to find the very lowest y value that exists on your function. Somewhere down here, I don't know where it is, I'm just estimating. So from this minimum value, the minimum y value, and then all the way up. That's the range of your function, okay? That's an arrow. I don't know what that was supposed to look like. All right? The way that you would write that down in inequality notation would just be y is greater than or equal to whatever that minimum number is. Okay? If you were writing it in interval notation, you would use a square bracket instead of a parentheses because your graph actually touches that minimum value. So you would do square bracket, minimum value, all the way to positive infinity, close parentheses. Okay? So how is the range different if you have an even degree and a negative leading coefficient? Well, your graph goes down forever, but we've got to have some sort of maximum y value. You're going to find your maximum y value, and you're going to use that as part of your range. Okay? Again, inequality notation, it's everything below that number, right? So when you're writing it down on your paper, you would say y is less than or equal to that maximum value. In interval notation, the very lowest value would be a negative infinity because we're going way down low. So negative infinity, comma, whatever your maximum is, close parentheses. Close your brackets. Okay? So this is going to be the only time we use a bracket when we're talking about range here. When you're actually hitting a specific number value. Infinities are always with parentheses. All right, now an odd degree polynomial is a little bit easier. It's going left and right forever, so that took care of our domain, but it's also going down and up forever. It's going to negative infinity and positive infinity. It doesn't matter if I start approaching positive infinity on the left and negative infinity on the right, or vice versa. The fact of the matter remains, our range values are still going to be all real numbers. So just stop and look at your graph for a minute. Which way are your arrows pointing? If they're pointing in opposite directions, both domain and range are going to be all real numbers forever. All right, flip your paper over. Let's go through an example. So we give you y equals negative 3x to the 6th power plus 3x cubed minus x plus 5. What is the degree of this polynomial function? Well, I can see that it's already written in standard form because our highest exponent is listed first, or that term is listed first. So the degree is the number 6. Is it even or odd? Well, the number 6 is even. So I know my end behaviors are going in the same direction. Our leading coefficient, that number attached to x to the 6th, is a negative 3. So because it's a negative leading coefficient, both of my end behaviors are going down. That's why this graph looks like that. So let's talk about these increasing and decreasing intervals. I'm going to go ahead and highlight again. So let's use blue first for increasing. I know that this section of my graph is going higher and higher and higher and higher, all the way until I get to that maximum value. What is that maximum value? Well, here it is right here. Okay? Now, am I going to use the x value, the y value, both of them, one of them? What are we always using? We're always going to use the x values only. So if you want to, go ahead and highlight those x values on your paper now so that you don't forget. We are only using our x values when we list these intervals. Okay, so our increasing interval, this first interval, starts way over here at negative infinity, all the way until I get to this value right here. What is that x value? It's negative 0.323. So we have an increasing interval from negative infinity all the way to negative 0.323, close parentheses. Okay, then I have another interval. Here, my graph is decreasing, and we're always listing from one x value to another x value. So we start with the x value of negative 0.323, where we left off, and then we put comma, and we go all the way to an x value of 0.348. That is where our function is decreasing. It's not telling us how high or how low it's going. I know it's decreasing, and I want to know where it's decreasing. All right, the next part of my graph is increasing right here. So from x value to x value, where is it increasing? Where is it increasing? Uh-oh, do we have that one written down? Oh yeah, it's negative. I went crazy there for a second. So we know this graph is increasing. So we use parentheses, 0.348, 0.348, comma, all the way up to 0.735. And then again, lastly, we have our function decreasing. This part of our graph is decreasing. It's going down forever and ever and ever, right? So what x values, where is it happening based on my x values? So from 0.735 all the way to the x value of positive infinity. Okay, so you should start with a negative infinity, finish with a positive infinity, because again, x values go from left to right. So let's talk about our end behavior. I told you we had sentence stems, right? As x approaches negative infinity, what is f of x approaching? It's also approaching negative infinity. Okay, as x approaches positive infinity, so as x moves further and further and further and further to the right, what is happening to our function? It's also approaching negative infinity. And again, our domain is going to be all real numbers. Our functions, our polynomial functions, go left and right forever. So we can write it using set builder notation. X is an element of all real numbers. Or we can use interval notation from negative infinity all the way to positive infinity. Now, our range value. Let's talk about range values. Remember, range has to do with y values. Range has to do with y values. I can tell that my very, very, very lowest y value is going to be a negative infinity. But what's the very highest y value? Well, I can see that this point right here is just higher than this one over on the right. So this point right here has the highest y value. Well, what is that y value? It's 5.218. This is the only time we use our y values when we're talking about the behavior. I don't want to say the only time, but this is when we're going to use this y value, 5.218. And that's only because we are talking about range. So are all of my y values greater than 5.218, or are all of my y values below or less than 5.218? We would say y is less than or equal to 5.218. And again, we can also use interval notation, and we always go least to greatest. The very lowest value is negative infinity. The very highest value is 5.218, and we use a square bracket here. All right, one more example. All right, y equals 2x to the 5th minus 3x to the 4th plus 4. The degree is 5, and our leading coefficient is 2. Again, our degree is 5, which is odd, and our leading coefficient is a positive 2. It's a positive 2, okay? That is why our end behaviors are going in opposite directions. We start low, we end high. Okay, so let's go ahead and highlight, or I'm going to go ahead and highlight anyway. We have an increasing interval, then we have a decreasing interval, then we have another increasing interval. And we're always going to use our x values. So I've got this x value and this x value. And our function moves from left to right, from negative infinity to positive infinity, left to right, negative to positive infinity. All right, so this first blue section of our graph right here is increasing from negative infinity all the way to negative 0.74. Then it begins to decrease from negative 0.74 all the way to positive 0.74. And then it begins to increase again right here from 0.74 all the way to infinity. Now, what are the end behaviors doing of our graph? So as x goes to negative infinity, as x moves really, really, really far left, what's happening? It's going down forever. It's moving to negative infinity. Negative infinity. And as x approaches positive infinity, so as x moves really, really, really far to the right, what's our function doing? What is f of x doing? It's going up forever. It's going up forever to positive infinity. So because this is an odd degree polynomial function, our domain is all real numbers, right? Or we can say it goes from negative infinity to positive infinity. And our range, lucky for us, is exactly the same. Our range is exactly the same, okay? Y is an element of all real numbers, or you could say it goes from negative infinity to positive infinity.